All right, we're going to look at kernels of ring isomorphisms. And so let's look at if you have a group homomorphism, the kernel is a normal subgroup. So the kernel of a ring, because ring homomorphisms are the same as group homomorphisms in some sense, they're just a special type, then the kernels are going to be normal subgroups. This is not too exciting since rings are abelian groups, and so every subgroup is a kernel. It'll be somewhat useful. Since rings are groups with additional multiplication operation, and ring homomorphisms are also group homomorphisms, the additional requirement that preserves multiplication operation, all kernels will be normal subgroups of the ring's group under addition. Okay, so that's not too exciting. We know that kernels of group homomorphisms are subgroups. And so, because ring homomorphisms are group homomorphisms, that means every kernel is going to be a subgroup. And since it's got to be normal because, one, it's a group homomorphism, but also because the group is abelian. The ring is an abelian group under addition. Every subgroup is normal, in summary. So let R be a ring, an element. Then we can look at this. So I'm conjugating here. This often looks like, we might often write this in group theory like that. So let's just see what happens. Since I can use the abelian nature of addition. So if you have something in the kernel, then of course you can conjugate and get something still in the kernel. So this is not terribly interesting. It's because we're in an abelian group. So for every element in R, when you conjugate something in the kernel, you stay in the kernel. Great, so the kernel is normal. We know that now. So we have a normal subgroup. Kernels of ring isomorphisms are normal subgroups when you are thinking about addition. We're going to focus on how the multiplication works with the kernel. This is pretty interesting. So again, let's look at something in the kernel of a homomorphism. Then notice A can be any element of R. X is in the kernel. So we have something in the kernel, and we have any other element, not necessarily in the kernel. I can use the homomorphism property for multiplication to get that. This is in the kernel, so I get 0. And 0 times anything gives me 0. So what does this mean? That means if you start with something in the kernel, multiply by anything else, the product is going to be in the kernel because it maps to 0. So you have this kind of absorption or sucking effect that when you multiply something in the kernel, you stay in. Similarly, if you multiply on the left, you get, right, that'd be an AX. That'd be AX, that'd be phi of A times 0, and that'd still be 0. So it works out. So we're going to make a definition based on this. A subring, this is actually a subrung. If you assume that rings have to have unities, then we're going to change this to subrung, because we're not going to require that ideals have unities. But a subrung ring is a two-sided ideal if you get AX and XI are in the ideal for all A. So this basically means it's a normal subgroup because, right, a subring or subrung of a ring is going to be a subgroup of R plus. And because this is abelian, every subgroup is normal. So we get a normal subgroup plus this absorption effect. And so what we see is that the reason why we're defining it this way is every kernel of a ring or homomorphism is an ideal. It's a two-sided ideal. So they absorb. So here's a theorem. Let's suppose you have a non-empty subset. Then the non-empty subset is going to be an ideal if A minus B is in there whenever A and B are an I. What this is it's basically GH inverse belongs to a subgroup H whenever G and H are in there. This is just a property of groups, basically. So this is just kind of a quick way of doing it. And you also need to have this absorption effect. If you don't want to check both of these, if this is kind of complicated, you can just think of it like, okay, well, you need to show that that I is closed under with respect to plus, and I contains its inverses. That's really what you need to check. You could either check these two or you could check that. Either way. So right, yeah, this is just basically it's a subring, and the second is an ideal. So we showed that all kernels are ideals. In fact, we defined ideals to be kernels, basically. We're going to show that all ideals are kernel. And we're going to do this by the first isomorphism theorem for rings. And this should be very familiar. If phi is a ring homomorphism from R to S, then R mod the kernel, and all kernels are ideals, so it is isomorphic to this. So this quotient is an image. And the proof is similar to the first isomorphism theorem for groups. It's nothing surprising. But the takeaway is, let's suppose you have an ideal. Then you have a well-defined multiplication. So you can look at the factor rings portion, but you can define a quotient ring where addition is going to be a plus b, and you can also define multiplication. Again, you need I to be an ideal in order for this to work out, just like you need normal subgroups for this to work out. So this is going to be true, and so the kernel of this is going to be everything in I, because I plus A is going to be equal to I if and only if A belongs to I. So that's basically what we can do. So every kernel is an ideal because we basically define ideals to be kernels. And if you have an ideal, you can mod out by it, and you're going to get a kernel. Let's look at some examples. Here we have a ring homomorphism. We've seen that it's already a homomorphism in the previous video. And the kernel was all multiples of 6. This is an ideal. It's a subrung. So, and then it's easy to check that it's a subrung. So if you have a multiple of 6, multiply by any other element. It's still going to be a multiple of 6. Right? If x times a is going to be 6y times a, 6 times y. So that's in 6z. So this is, the absorption property might seem a little weird, but it isn't all that weird when you think about multiples of 6. If you multiply a multiple of 6 by anything else, you're going to stay a multiple of 6. Similarly, do it on the other side. So in fact, this is an ideal. We've seen this homomorphism before. We're going to see that the kernel is an ideal once again. Remember, the kernel was 0. So this is pretty clearly going to be an. So we certainly have 0 times anything. It's going to give you 0, so that works. 0 is always an ideal. Here's another example we saw. The kernel was, once again, 0. So basically, by the same reasoning as up here, we get zeros in ideal. Here's another one. Polynomials to the integers, which we saw earlier. What's the ideal here? Well, the kernel was this. Is this going to be an ideal? Well, I have something in the kernel, and remember, there's no constant term, so the smallest degree has an x. If I multiply it by this, when I multiply these two together, I could imagine I could factor out an x out of all these, and I get x minus 1, and that would just go away. But then I'm going to get x times some polynomial. But x times some polynomial won't have a constant term. So therefore, the result will still be in the kernel. And likewise if you multiply in the other direction too. So there is no constant term because the constant term would be a1, b0, but then I multiply by x. So the smallest degree term is going to be a1, b0 times x. And that's in the kernel because the kernel says that the constant term has to be 0. Thanks, we're done.